guys, how you doing? I hope you're doing well. Again, we're going to continue with lecture 4, using questions from exam 1. So let's get into what we need to talk about in lecture 4. I'm going to go ahead and skip ahead of the review questions because we already did those. And get into stoichiometry. Stoichiometry is a big word, and it's most of what we do in the first half of chemistry. Stoichiometry is the only way to determine how much of a second reactant or product we get if we know how much of one thing we started with is by using the molar ratio. So what the heck does that mean? Well, let's talk about the molar ratio first. The molar ratio is the ratio of the number of moles of material to the number of moles of another material in the balanced chemical equation. For instance, 2H2O plus O2 goes to 2H2O. Okay, awesome. The ratio of H2 to O2 is 2 to 1 because there are 2 H2s and 1 O2. The ratio of O2 to H2O is 1 to 2 because there are 2 O2s for O2. There's 1 O2 and 2 H2O. So what does that mean to you? The first thing you do in any calculation that you get is to write or have a balanced chemical equation. Now, if you have to write one, then you write one. If you get given one, make sure it's balanced, because if it's not balanced correctly, then you're not going to be able to do the calculations the way they do. So always make sure that you check them. Alright? Oh, look at this. This is the stoichiometry mole island diagram. When in doubt, convert to moles. You'll hear me say this over and over and over again. Now, if I know a mass, then I can get to moles. If I know how many particles, I can get to moles. If I know mass, I can get to moles, I can get to particles. If I know particles, I can get to moles, I can get to mass. We'll talk about the volume of the gases much later. Alright? Once I have moles of substance A, then I can use the coefficients from the balanced equation to get from moles of A to moles of B. And that B could be another reactant, or it could be products. It doesn't matter. And of course, once you've got moles, you can go to the mass of that material, you can go to the number of particles of that material. Alright? So that's how we're going to look at that from now. Let's talk about this. Now, we need to talk a little bit about how we normally find elements before we continue. Because in order to write these balanced equations, we need to know what state some of these things are in. There are a couple of them we really need to know about. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay? And then we can list them as hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Have no fear of ice-cold beer. It's a mnemonic. It's supposed to help you remember which of these things occur as dimers. They don't naturally occur on their own. They're always dimers. Okay? So we need to be able to talk about that. And they're almost always in the gas phase. Okay, cool. Awesome. Obviously, I'm going to need to use that. How? Let's talk about stoichiometric calculations. Industrial ammonia is produced from reacting hydrogen and nitrogen. If I have 16 grams of hydrogen, how much ammonia can I make? First, we have to assume that there is enough nitrogen to do this. Okay? If that is not the case, we'll talk about how to handle that later in this lecture. So we're going to write and balance the equation. So H exists as H2, N exists as N2. That produces liquid ammonia. H2 gas plus N2 gas goes to NH3 liquid. But that's not balanced. I have 2 nitrogens on the reactant side and 1 on the product side. So let's balance that. In order to make the same number of hydrogens on both sides, I have 2 on one side, the reaction side, 3 on the product side. Then we're going to multiply to get the nearest common denominator, which is 6. So I have 3H2 plus N2 going to 2NH3. And of course, 6 hydrogens on the reactant side, 6 hydrogens on the product side, 2 nitrogens on the reactant side, 2 nitrogens on the product side. The next thing I need to do is convert the mass to moles. When When in doubt, convert. Sorry, I apologize. So 16.0 grams of H2 is divided by 2.02 grams of H2 per mole of H2. That gives me 7.92 moles of H2. Now it's 3 sig figs because 16.0 has 3 sig figs. Okay? Awesome. Now we have to go, so we converted mass to moles. Now I have to convert from moles of H2 to moles of NH3. So 7.92 moles of H2. There are 2 moles of NH3 for 3 moles of H2. That's how we use that information. It's just another conversion. Okay? So if I do that happy math, that gives me 5.28 moles of NH3. Again, limited to 3 sig figs based on the 16.0 in the original calculation. From there, we have to convert from moles of NH3 to grams of NH3. 5.28 moles of NH3, there's 17.04 grams of NH3 per mole. Okay, awesome. That gives me 90.0 grams of NH3. Woohoo! Now, I could have written this all as one calculation, and this is typically how I set things up. I always start with whatever number they gave me. 16.0 grams of H2 is what they gave me. I get rid of the grams of H2 and convert to moles. So divide by 2.02 grams of H2 per mole of H2. Then I need to get rid of the moles of H2. I do that by using the ratio. So 2 moles of NH3, what I want, over 3 moles of H2, which I need to get rid of. I then need to go from moles of NH3 to grams of NH3. And I do that by multiplying by the molecular weight of NH3. Okay, moles cancel, grams are left. That's what I was looking for. So 90.0 grams of NH3. Again, 3 sig figs gives you 90.0 grams. Okay? So that was all of the detail, and that's the big parts and how you would do it as one calculation. And remember, every step that I did, I rounded what I reported, but I keep all those decimal places so that I make sure that I don't have any rounding errors at the end. So that's how these calculations are going to work. Now we're going to practice a bunch of them. So here are some example calculations that we're going to do. Talk about sulfuric acid reacts with sodium hydroxide to produce sodium sulfate and water. If 500.0 grams of sulfuric acid is used, how much sodium hydroxide is required? Okay, sweet. Let's give me something to write on. And of course, we'll need a calculator. So let's do that. What does that say? Sulfuric acid. Sulfuric acid. Sulfuric acid is H2SO4, and I know that because sulfate is SO4 2 minus. So if I have SO4 2 minus, I have to have 2 protons on that, so that's sulfuric acid. Awesome. Reacts with sodium hydroxide, and that gives me sodium sulfate and water. Sodium sulfate. Since this is a 2 minus, this is a 1 plus, I need a 2SO4 and water. Okay. H2 and the H here, that means 3 H's. Okay, awesome. Not exactly cool. Let's start with our Na. So I have 1 Na on the reactant side, 2 on the product side. So let me multiply this by 2. Okay. Once I do that, then I can look at the sulfurs. I have 1 sulfur on the reactant side, 1 on the product side. Na is good, S is good. H. Let's see, I have 2 H's there and 2 H's there, so that's 4 H's. Don't have that over here, so I'll multiply by 2 there. Now I have 4 H's on the product side as well. I have 4 oxygens here, 2 oxygens here for a total of 6. I have 4 oxygens plus 2 oxygens, total of 6. So that is a balanced equation for this. Now it says that I have 500 grams. 500 H2SO4. And I want to know how much sodium hydroxide is required. And then 190 grams. Okay, it didn't actually tell me that, but that is what I was looking. Okay, fine. So I've written the 500 over the H2SO4. I've written the question mark over the NaOH. That tells me that those are the two species that I'm going to be working with. I always start with what I was given, 500.0 grams of H2SO4. And then I need to convert that to moles. In order to convert it to moles, I need a molecular weight. Now, I can do that as a separate calculation, but it's going to be 2 times 1.01 grams per mole. It's 4 times 16.00 grams per mole plus the sulfur. And again, sulfur being number 16 is 32.07 grams per mole. And of course, these grams being on the bottom means that the mole is going to flip. So I'm going to end up with an answer that is in moles. Awesome. Moles of H2SO4. Now, I didn't give myself enough space, so this is continuation of what I had. So I had moles of H2SO4 as a result of what I did here. So grams gets rid of gram. Moles of H2SO4. 1 mole of H2SO4 for 2 moles of NaOH. Sweet. And of course, if I want grams, I need to get rid of the moles of NaOH. And in order to do that, I need the molecular weight. So sodium, again, being number 11, is 22.99. And actually, I need to remove the per mole because I've already got that written below. So we're just going to be talking about the grams. Plus 16.00 plus 1. And that should give me an answer in grams. And I actually removed the grams and put it outside of the parentheses so I didn't have to write it every time. It's a little neurotic and crazy to do. So let's come over to our calculator. Let's turn our calculator on. 500 grams divided by 2 times 1 plus 4 times 16.00 plus 32.07. Multiply that 2, and then multiply the whole thing by 22.19 plus 50 plus 1. It gives me 407.787. Okay, how many sig figs do I need? Well, I started with 4, but the 1.01 is 3. So I'm going to need 3 sig figs. That means my answer is 408 grams. Okay. That's how much NaOH I require to be able to convert all of that H2SO4 into product. Okay? So that's that particular calculation. Awesome. nitrogen trichloride reacts with water to form ammonia and hypochlorous acid. If 125 grams of nitrogen trichloride is used, how much ammonia is produced? Okay, awesome. Let's see what we got. So, nitrogen trichloride, NCl3, reacts with water to give me ammonia, NH3, and hypochlorous acid, which is HOCl. And yes, you could probably look that up. It's usually how we do it. So I know I have one nitrogen here, one nitrogen here, 3 chlorines here. That means I need 3 over here. So that gives me 3 hydrogens, 6 hydrogens total. So I'll multiply this by 3. So 6 hydrogens on the reactant side, 6 total hydrogens on the product side, 3 oxygens on the reactant side, 3 oxygens on the product side. Okay, so that's my balanced equation. 125 grams nitrogen trichloride is used. 1, 2, 5 grams. And how much ammonia is produced? And again, I put this as a mass. Okay, awesome. Well, again, when in doubt, convert to moles. Start there. 125 grams NCl3. Divide that by the total for nitrogen trichloride. Nitrogen is 14.1 grams. And then we have 3 times 35. 5 grams. And 1 there. I know that there is 1 mole of NCl3 and 1 mole NH3. Is it necessary for me to include that in this calculation? No, absolutely not. It's a 1-to-1 ratio, so why does it matter? It doesn't, except for the factor label method. In order for me to be able to cancel, so I can cancel my grams here, but in order to be able to cancel the moles, I have to do that. And then that gives me moles of NH3. Now, a mole of NH3 is 14.01 plus 3 times 1.01 grams. And that will then give me the answer in grams. Okay, so I've canceled this, and that gives me grams of NH3. Alright, let's see if we can do some calculations with that. 125, divide that by 14 plus 3 times 3.45. Because I am that neurotic. And then times 14.1 plus 3 and it gives me 17.7 grams. Yeah, sig figs, because that's what I started with when I was 25. It's also what I have from the mass of the hydrogen. So 17.7 grams of NH3. That's how much I produce. oxygen reacts with propane to yield carbon dioxide and water. If 25 grams of propane is used, how much carbon dioxide is formed? Well, alright, here we go. Again. So oxygen, O2, reacts with propane. Propane is C3H8. Gives me CO2 plus H2O. And this is actually an equation that we balanced in a review. So this is something that you guys have already talked about. So the 3 carbons, because there's 3 carbons here, I have 8 hydrogens. So I need to multiply this by 4. That gives me 8 and 8. That gives me 4 oxygen there, plus 6 is 10 oxygen, so this needs to be a 5. Okay. Ooh, I balanced that. Alright. I have 25.0 grams of propane that's used to do this. I don't know how much carbon dioxide. When in doubt, convert to moles. 25.0 grams C3H8. C3H8 times 12.01 plus 8 times 1.01. I know that there is 1 mole C3. H8 here, and that's 3 of CO2. In that 3 moles of CO2, plus 2 times 16 grams. If I do that, I should write 0 divided by 3 times 12 plus 8 times 1.1. Yes, I know, I didn't actually need to do it, but it won't sit right with me if I don't. Let's do times 50. And that gives me 74.88. Now again, 3 significant figures because that's what I see in the 5. So that will give me 74.9 grams of CO2. No, really, that's supposed to be CO2. Okay, questions about that? Awesome sauce. And yes, I'm going to delete this because I like clear games. Alright. Carbon disulfide reacts with oxygen to produce carbon dioxide and sulfur dioxide. Using 152 grams of carbon disulfide produces how much sulfur dioxide? Alright, let's find out. So again, come over here. Carbon disulfide reacts with oxygen to give carbon dioxide plus sulfur dioxide. sulfurs. So I'm going to multiply this by 2. That's 2. That's 2. Now, I have 2 oxygens from the carbon dioxide, and now 4 oxygens from the sulfur dioxide. 2 plus 4 is 6, which means I need 3 of those. Okay? If that's true, and I need 152 grams of the CS2, then I'm going to know how much sulfur dioxide. Well, let's check that. 2 grams CS2. CS2. And this is going to be 12.1 plus 2 times sulfur is 32.07. Well, that's not going to work. So I'm going to have to move that. So let's erase this part first. See, my units didn't work, and that's why I have to do this. Which makes perfect sense if you know what you're doing. You're like, yeah, why would you do that? You mess up. Yeah, I did. Way too much. And this is 2, 0, 7 per mole. CS2, 2 mole. SO2, 1 mole. SO2. And then that's going to be 32.07 plus 2 times 16 grams. Okay, awesome. $255.775, and of course, how many sig figs is that? Well, it's 3. So, 3 sig figs. And that's limited by the 152 that we started with. So even though we have more decimal places or more sig figs available in the masses that we're using, that's not going to translate because of the 152. So 256 grams of SO2 will be produced from that. Okay, awesome. So we can do that. That's fabulous. I'm going to clear this. Put this down. Clear this. Put this down. Let's go here. Anyway, questions, comments, problems. Again, if there are questions, comments, problems, please reference the lecture number, this lecture form, this timestamp, and then your question or comment, and submit that to me via email during office hour. slide 9, when I said that we would consider what happens if there isn't an excess of nitrogen, remember that time is now. I liken this to hot dogs and buns. Have you ever noticed that buns come in a package of 8, but hot dogs are sold in packages of 5? Why is that? Well, okay. It's really to make more money. It's to force you to buy multiples of both. Because if you don't buy multiples of both, I can only have a bun for each hot dog. If I buy 5 packages of buns and 4 packages of hot dogs, it's the only way I can get an even Steven thing out of it. Otherwise, I have either too many hot dogs or too many buns. But let's think of the implications of those size limitations. If we only buy 1 package of hot dogs, we will get 5 hot dogs with buns. If you buy 2 packages of hot dogs, you will get 8 hot dogs with buns. In the first case, you're limited by how many hot dogs you have, because you only have 5 hot dogs. In the second case, you're limited by the number of buns that you have. So you only have 8 buns, so you can't make 10 hot dogs. Either way, there is a factor that limits how much finished product you can make. Limiting reagents are that same idea. It's a way for us to figure out what we don't have enough of. And that's really what it comes down to. Right? So let's see how that works when we need to talk about it. And it's always done as a calculation. Illustrated example. Let's consider again the reaction from slide 9. So we still have 3H2O plus N2, 2NH3, and 16.0 grams of H2. Let's say for the sake of argument that we have 16.0 grams of N2 as well. How much product can we make? Well, sorry, I made a mistake when I was typing this. Forgot to do something I needed to do, so. So again, 90 grams of NH3 were made if we had 16.0 grams of H2. 16.0 grams of N2, we're going to have 28.02 grams of N2 in a mole. So my grams of nitrogen will cancel. So my grams will cancel, and now I have units of moles. 1 mole of N2 on the top, 1 mole of N2 on the bottom, because I'm here, to 2 moles of NH3, because stoichiometry says that. 1 mole of NH3 is 17.03 grams of NH3. And that equals 19.5 grams of NH3. That's what we make. So interesting. Even though we have the same amount of each reactant, we do not form the same amount of the same product. That's because the molar ratio is different, because the molar mass of the reactions is not the same. So one of the reactions limits the amount of product that we can make. Which one is that? That's right, it's the N2, because I produce less NH3 from that. So it's the limiting reactant. Okay? Now, a note for you. There is no way to predict from a balanced equation which material will be limiting. It is not possible. Okay, you can try it all you want, but it isn't going to work. Because of this, if you're asked what material is limiting, you must do the calculation and find out either how many moles of product or how many grams of product that you will form. And it should be the same product. So again, we talked about this in the last slide, and we were considering making NH3. We can go to moles of NH3 or grams of NH3. But it doesn't matter, because both of those will take into consideration the things that we need to take in. Okay? So the mass of the starting material and the ratio of the starting material to in this case, the product that we're looking at. Okay? So it doesn't matter if you go grams or moles. I usually go grams, and the reason that I do that is because we're almost always asked how much we form in grams, so that's why I do it. Okay, but it really doesn't matter. If they just ask you which one's limiting, you can do it. So excellent. Now I can predict the amount of product I'm going to make. That's fantastic. Now, the number that you calculate is what we call a theoretical yield. That implies to me that there is an actual yield of some kind, because that's sort of the opposite of theoretical, right? Yeah, it is. So let's talk about actual and percent yield. So what I actually produced is called an actual yield. Almost all reactions are reversible, meaning that not all material is converted to product. So you make some product, that product goes back to make reactants. It's an equal amount, we'll talk about that later. But that's what happens. Products can react further to produce other materials, okay? And that changes the actual yield of the product you want. Recovery of the product you want may be difficult to do without some losses. So depending on what state it's in, what that process is, it may be very complicated to get everything that is produced. Okay? So if the actual yield doesn't if the actual yield doesn't equal the theoretical yield, and hint, it never will, then chemists want to know how efficient the process is. We determine that by calculating something called the percent yield. Percent yield is given by actual yield over theoretical yield times 100. Now here's an interesting factoid for you. Surprisingly, ammonia is difficult to produce, and the industrial process used, which is called the Haber process, is usually only 28 to 29% yield. 28 to 29% yield. So that's like a quarter of what you think you should be getting. That's pretty amazing to me. I mean, this is something that we do all the time. You know, we create ammonia that can be used to clean your house or whatever you use it for. But that's a really inefficient process, right? Actually, that's pretty high. Given a lot of things, that's pretty high. So that's what we're talking about in terms of yield. Okay? Questions about what those things are. Again, if you have them, please make them at a time and a lecture number. Let me know what your questions or comments are, and we'll take care of it. And that's it. So I didn't give you any practice in calculating percent yields, but that's how they're defined. So that's everything out of lecture 4. We're gonna take a break now, stop with lecture 4, and then we'll come back to lecture 5 at some point. I hope that was clear to you guys. If it's not, let me know, and we'll see what we